Okay, let's start the next and final lecture for this series. This one is final one is, as I said, interface engineering of organic semiconductor. I was telling this term frequently when I deal about all the makes, especially when you make an organic solar cell. Okay, so now this interface engineering is really helpful to improve to make a best devices, because in overall, if you see that all those in this material, design is very important according to applications, which band gap you are using and which homo level you are using, everything. Okay, we got a material and we got all photophysics and everything. Okay, then we make a good device, and interface is very important both in OLED, any device you said interface, because why is it important means still the charge extraction and charge injection is inorganic, but all the photophysical process happening in organic. So the organic inorganic things now both are entirely different one. We need to have a suitable interface layer for efficient performance. Okay, I think you can understand, because when you go from entirely new material from one to another, we need to have a good transition. That's what interface engineering doing. Okay, so everything is a play of energy levels manipulations, all those things you have to understand, because even the same architecture, the same electrode, just changing the different energy levels of interlayer, we can change the which charge you want to extract. For example, the ITO, if you quote P dot, that is for hole extraction. The same ITO, if you do zinc oxide, or if you do TiO2, or if you use tin oxide, the same ITO will get electron extraction. You got to understand. So that's because of the interface engineering. That's how we are going to do. Okay. Okay. Yeah, I'm going to cover this thing. First thing I'll say, what is the different architecture? Mainly, the thing is mainly two different type of interface engineering. One is a hole transport layer, that's from anode, and other one is cathode interface layer. That's from electron transport for cathode side. So those things, there are different types. One is organic type, the other one is inorganic, only two things. So there are metal oxide, that is inorganic hole transport layer, and organic, both small molecule and polymer hole transport layer. In ETL also both is similar. Okay, this is the one maximum. Even though there is different interlayer materials are available, everything we can classify in these four things. Okay, in addition to that, hole transport layer, electron transport layer, we can call it as another one is a electron blocking layer, a hole blocking layer, to further introduce changes. For again, the electron blocking layer means nothing but is a hole transport. There's just as one. Okay, I will go through that when I deal the devices. Okay, now. So now, why this is important? When you make this device an efficient device, mainly we can go for a large area. This is the benefit of organic solar cell. Mainly, we want to improve if you want to improve the PCE, power transfer efficiency, JSC, fill factor. These three things we need to improve. Okay. We know that VOCs, we can, any two material, the VOC is fixed, only we can get homo of donor and lumen of acceptor. That we can't do anything with the lumen. When you fix a two material, the VOC is fixed. Okay, but we can fine tune the performance, increase the JSC and the fill factor, we can increase further, provided if you give the good interface. If you do the good interface, these two things, these two parameters, JSC and the fill factor, can improve. Again, we will get the efficiency improvement. Okay. So why I am saying that the VOC is fixed between these two material. Still, there is a room to improve the efficiency, because if you do the interface is correct. Okay. Because ideally, we want to give ohmic contact. Ohmic contact means almost very little barrier to charge injection or charge extraction. It's called ohmic contact. Then it should be a very, very thin layer, because if it is too thin layer, because any organic layer or metal oxide, this is not a metal, this metal oxide is a semiconductor. This semiconductor is conductivity is slightly lesser than if you compare the conductor. Okay, if your thickness is higher, eventually introduce resistance. Okay, that's why we make it the interlayer as thin as possible. Okay, and we can also, in addition to a hole transport layer, we have a blocking layer here, so that we have to only extract electron, extract holes in this side. Sometime when the exciton come, there will be a lot of charges go here and there. Electron also come here. So the electrons should be blocked this side. We got to extract only holes, anode side. So we have the electron blocking layer this side. Similarly, the other side, we want to extract only electron, but the hole also can come over there. That should be blocked to have the better efficient performance. Otherwise, if the holes is come this side, that will recombine, then reduce the performance, particularly reduce the energy levels. Okay. So we can have the, ideally we want to have the metal oxide. Why we want to have the metal oxide interlayer over organic layer means metal oxide is already oxidized. We cannot have oxidized again. So that it will give the good protection layer for organic, because one of the major problem with the organic material is it will easily oxidize when you put oxygen. Okay. If you cover this organic layer with the metal oxide, then metal oxide not only extract the electron or holes, at the same time it protect the active layer from further degradations. That's why metal oxide interlayers are preferred over organic interlayer. Okay, especially for stability and efficiency wise. Hope you got that. Okay, next thing is I'm telling the different architecture. So this is if you have a standard architecture, only we have the 5-layer devices. Said active layer, 2 cathode and 2 interlayer, 2 electrode, anode and cathode, and 2 interlayer, hole transporter, electron transporter, 1 active layer. The active layer is a blunt, is a bulk heterojunction layer. So whether it should be anode is a bottom electrode, then it will have a, if it is anode is a bottom electrode, then it's called a regular or conventional geometry. If it is a bottom electrode is cathode, then it will call inverted geometry. Here if you see that if you do P dot PSS, the same ITO is anode. If you have the zinc oxide or tin oxide, the same ITO can be considered as a cathode. It will act as an extracting electron. So again, lithium fluoride, zinc oxide in top is cathode here. Here we use a moly oxide. Just changing the interlayer, you can change the structure of the, we can change the functionality of the devices. Here by just changing this brown layer, we can extract holes this side. At the same time, the same ITO electrode, we can extract the electron. So interface layer is very important to decide what carrier you want to extract or what carrier you want to inject. Okay, that's why this is a very special term, interface engineering. Okay. So if you see one example here, how the interface is working. For this device, if you can able to devise on only purely top of ITO without P dot PSS, we are getting very low VOC, only 0.5. At the same time, if you introduce a P dot inside, if you have ITO and P dot, you see how much VOC. Yeah. Okay. So this P dot especially adjust the energy levels fast, so extract etc. It's not only improve the current, it also improve the VOC. That is the, so without any interlayer P dot, it's giving a performance of only 0.67. With the P dot, the efficiency nearly go up to double. So that's the beauty of this interlayer, effect of interlayer actually. So next, again I'm going to show the few example about even if you go to choose interlayer in best efficiency. I'm giving the example. P dot is one of the interlayer, and the moly oxide is another one. If you compare this one P dot and moly oxide, somewhere moly oxide will give at least a good fill factor. As I said, the quality of the device is determined from the fill factor, because fill factor says that the squareness of the J-K curve. If you get a very good square, then your device is highly optimized and very good devices. It can stable for a long time. So if you have a high fill factor, squareness is very high, then efficiency also will be very high. So whenever we used moly oxide as a hole transport layer, we always see the performance improvement. Okay, and also this moly oxide is very good comparing to P dot PSS. Why is it? Means moly oxide is a metal oxide which can protect from environment. At the same time, P dot is the polyethylene dioxide thiophene, which is a water-based hole transport layer, and the PSS polystyrene, sulfonated polystyrene, PSS sulfonic acid, that is an acidic material. Okay, normally for the long-term effect, this type of acidic one can start react with the ITO, because these are all coated on top of ITO. When ITO, this acid will react to the ITO, then it will corrode the ITO. So in future, for real fabrication device, we don't prefer P dot PSS, or we only prefer metal oxide interlayer. Okay, but for testing purpose, when you found new material, for testing devices and making short-term device is a very good PDOT because it's readily available. We can easily spin code and easily do that. For processing, it's simple, but for actually in production case, we'll go for the metal oxide interlayer. Particularly, we go for zinc oxide layer for inverter architecture. I can come back to it later. So this is one of the things. The other one is we try with the CuPC and moly oxide is another one. Here also we can see the improvement. Whenever we use the moly oxide, the performance is particularly we can improve the things in fill factor is improving. But other factor also improving, that is little bit. But fill factor improvement is always increased when you use the moly oxide. And in this case, aluminum PC chloride, aluminum thiocyanate chloride also we can see that improvement. So in the case for whole transport layer, in many cases, many combination of things, the metal oxide, moly oxide, molybdenum oxide is giving equivalently good performance. The other one, I can talk about all those whole transport layer. Not only this one moly oxide, there is a nickel oxide is there, then vanadium oxide is there, then tungsten oxide is there. These are all acting as a whole transport layer. Everything is in such a way that giving equivalent performance. Okay. So whenever we use for large area processing, we go for metal oxide rather than PDOT PSS. Okay. Okay. So we see that all these device performance, I said moly oxide is the best performance. Why? So we want to explore further. Why is it doing? Again, it's a tuning of energy levels. Mainly things up, because I said energy levels, in order to extract smoothly the holes in this one, the energy levels should be channelized because we know that water can easily flow from top to bottom. You don't need any effort, it will automatically flow. But if you want to do anything, so bottom to top, we have to put any external force to move it up. Like this, we make an energy level so that these holes can easily go up. We can arrange the energy level in such a way that it can easily go through, arrange the energy levels in such a way to high to low, then hole will be easily extracted. Like this, what we are doing, if we have the ITO only aluminum PC, if you see that work function shift is only 0.2, only slight shift, that's not enough for hole extraction. At the same time, when you introduce a moly oxide in bit, we can see how much shift, around 2 EV shift is there. We introduce specifically the vacuum level shift is, here is only 0.2 to 10, nearly 10 times higher shift is by introducing moly oxide. That's the reason we are getting why this moly oxide giving the efficient charge extraction and how is it helpful for efficient performance as well. This UPS studies, I think with this UPS we already gone through that item. You understand now very well what is the cutoff region, what is the HOMO region. If you see this one ITO, if you go ITO, the secondary cutoff Fermi levels are 6.1. When you have only the CuPC layer, the difference here to here is very, very less. Okay, but when you put a moly oxide, you see how much shift is there. It's nearly 15 to 16 point, more than 1.2 EV shift is coming in the work function itself. That makes the charge extraction is easier for whole transport layer. Okay, and also there is a difference in the HOMO level as well. By seeing the work function shift itself, you can see that the energy level is changing just putting the moly oxide. You see the moly oxide is only 50 angstrom. 50 angstrom is nothing but it's a 5 nanometer is good enough to make a efficient charge extractions. Okay. So these are all, as I said, these are all is playing around with the adjusting the energy levels with your electrode and your organic layer. Okay, both are in different layer. The interface play a major role adjusting these energy levels. Okay, and this one will give about some of things. As I said again, in addition to whole transport layer, electron transport layer, we need to introduce a blocking layer. So, for example, this slide, if you see that the exciton is generated because of this built-in function with the ITO and cathode, the holes should go to anode and the electrons should go to cathode. This is a natural process, but some of the electron, instead of going cathode, it's come to anode as well. But some of the holes, instead of coming to anode, it can go to cathode as well, like this. Okay. So here the holes should be blocked. Here the electrons should be blocked. That's why here we need to introduce the blocking layer. Okay. To introduce a blocking layer, what we try this another TFP is another molecule we introduce here. This will have a very high very high the LUMO level. So when you have very high level, the electron will be blocked here. If you have the energy very high. That's why when you go the moly oxide, on top of moly oxide we coat TFB. On top of TFB we have the active layer and lithium for aluminum. And we can see the device performance. When you have the moly oxide is 4.9. But again when you have the double layer, we have the whole transport layer and whole electron blocking layer. Okay, then we got a fill factor improvement and we have the device efficiency improvement. So always that improvement will be little bit only. This will be very minority cases. This type of this misguided charge carriers, because it should be only the whole only comes, right. This type of electron is misguided to anode. So this extra electron will be blocked because of this higher LUMO energy levels. So still we are getting the efficiency improvement by introducing the whole blocking layer. Okay. Hope. So this will giving the good understanding of why in addition to whole transport layer, why we need a electron blocking layer we want. Okay. Just because of to stop the misguided charge carriers. Okay. And also this is phase separated nanoscale phase separation of active layer. And when you have this multiple layer, and one more thing, the electrode will become more planarized when you have the coating of double layer. So that will make a very smooth layer and make a very good active layer film as well. There are multiple effects when you have the double layer, because this moly oxide is more crystalline and inorganic material which have induced roughness. So this roughness in the holes and all highly fill up when you coat another TFP layer and become more planarized when you do the double layer. So there are two ways. One is making surface smooth. Another one is making energy levels perfect. Okay. So this device more or less, in addition to OPV photovoltaic, when you make a photodetector we want to reduce the dark current, because in photodetector we don't worry about how much current is giving, more concentrate on how much restrict the dark current, because when you have because it will only detect the photon. When it is dark, it should have very, very low current. It should not generate current lot. So that is for that concept at very dark current, the whole blocking layer play a role to reduce the dark current. Okay. In photodiode it will be having a huge role in the fabrication of those devices. Okay. Again, we studied this moly oxide effect in different layer, because previously we have seen that aluminum PC and the P3ST device, how the moly oxide is working. So this case, what is moly oxide? Because when you see that whenever changing the PDOT PSS moly oxide, we have seen that fill factor improvement and efficiency improvement always. Again, we are going to deduce why this change is occurring. As I said, it's only because of the energy level changes. As I said, if you see the UPS cutoff region, in this case, when you have DTS, according to thickness, 1 angstrom, 2 angstrom, this 4 angstrom, 8. If you have about 16 angstrom, means it's around 1.6. From 1 angstrom to 15, it will have the huge difference. When you increase the thickness around 32 or 6 nanometer, 6.2, the secondary cutoff increase is almost saturated. Even if you go for beyond 6 nanometer, there is no difference. Okay, there are critical thickness we need to make a good energy level shift. So mainly 5 to 10 nanometer. If you put more than 10 nanometer moly oxide, then it becomes insulated. We can't put more than 10 nanometer, but the UPS research is saying that secondary cutoff 6 to 7 nanometer is good enough to introduce good energy levels in these devices. We can see that up to 1 to 2. And also we have seen that some of the HOMO energy level, we can see around 1.5 and small gap is forming around 3.2. So what this gap state is saying that no, because whenever we introduce this moly oxide on top, so there is a, when you introduce this one, there is a charge transfer from active layer to moly oxide. When the electron is traveled from here to here, then moly oxide is more electron. This is how some of the depletion region will form. What do you mean by depletion region? Then active layer become less electron, this is more electron. When you have the more electric field here, it automatically attracts the holes towards that. Then it will helpful to extract more holes. Because initially, because of moly oxide, it will electron will transfer from here to here and make a depletion region, and that called, in other words, we can call it as a band bending, because we say more electron is here. The electron is eventually which attract the Hall holes. That means we extract the electron by attracting that one. Like this, band bending is causing the efficient charge extraction. So those signature we can see it from this gap state. Okay, there is a charge transfer. There is a signature for charge transfer, and the gap state will link to the charge transfer of the active layer and the moly oxide. Okay, hope you can understand the mechanism, what happening, why is giving improved efficiency charge extraction in this case when you go to moly oxide. It's all playing a role with the alignment of energy levels at the interface. Okay. Okay. So this one you can see moly oxide is giving N. This again when you put TFP, it will block the electron actually. Okay. Next case is we are seeing that how some of the material we found that some devices we make a standard regular architecture. I said if you extract a hole from bottom side is regular architecture. If you extract the electron from bottom side is called inverted architecture. Here we found that the same material we fabricated device with the conventional and the inverted architecture. When you go for inverted architecture, the current is increased from 12 to 16. Okay, it's almost more than I think 30% improvement in current, and mainly the current is increasing, and eventually the performance of the device is increased 4.9 to nearly 6%. So we are exploring why this inverted architecture giving a good performance. So again, when you do this one, particularly for DTS, BTD, this polymer and PCBM, we studied. What we did is we coat this material and we take this one is high vacuum and use the organ sputtering. We can use the organ sputtering and we can start sputter, and when you go sputtering this one, we can remove the layer. By etching 10 nanometer and study the OJ electron spectroscopy, what is the element is there. Like this, we can keep on etching until the bottom layer. So this is around 80 to 100 nanometer. For every 10 nanometer we etch, we study what is the material is there. Again 10 nanometer study what is the is there. Like this, we can do the depth profiling. So depth profiling will say that what is the vertical distribution of your donor acceptor thing, because your active layer is a donor acceptor blend. It will arrange in nanoscale phase separation and horizontally. What is vertical? Because all the morphology is buried underneath the layer, so we can explore the donor acceptor combinations by doing the depth profiling. So the depth profiling shows that at the very surface, your carbon is very high. So if you see the DTS, BTD and the PCBM, PCBM is more carbon content. There is no sulfur in the PCBM, right? But in this material, there is how sulfur is there. Sulfur is not there. So we detect sulfur. If there is sulfur detection is there, that belongs to your P-type polymer. If you detect the carbon, that belongs to your acceptor. That's why we are seeing that when you go from the surface from 0 to 80 nanometer, at the surface, your sulfur is more, where the carbon is down, very less. At the surface here, your polymer is more, your carbon is still there, but when you come to this is 100%, is 50% reduced. When the sulfur is it is more. But comparing to the rest of the layer, in the down, if you go down, the sulfur is very, very low and maintained like this. Whereas in carbon is maintained throughout the things, because carbon is, PCBM is very small. Only if you can the surface layer, your polymer is more on the top and your PCBM is more on the bottom side. So this vertical arrangement is favorable for if you have the inverted architecture, because N type is all the electron will be generated come to this phase. If the bottom is for electron extraction, then it will be efficiently extract electron instead of going out from here to top. The top piece is polymer, there your hole is coming. If you extract the hole from the top, because all the majority of polymer in the top, the whole extraction will be easier if you are extracting the holes from the top. That's why in this case we have particularly in this configuration, the inverted device is giving high performance because it's naturally the polymer is arranging in the top layer and your PCB is bottom layer. So in this case, your inverted architecture is work efficiently comparing to the conventional. In the conventional architecture, the bottom layer is P-type, but your more PCBM ones on the bottom, then it will then it will more recombination is happening at the bottom side. That's why we got a very low current in this case, because a lot of charges will recombine because of the mismatch of your donor material as well as the electrode. Okay, I hope you got. Because of this vertical arrangement is also very important to design the, because this property we can't easily say that. Some of the things will naturally align, p-type is the bottom, some things arranged. Particularly for PCBM case, inverted architecture is best comparing to the regular architecture. Okay, I think you hope where we can choose the accelerator. So if you know the vertical distribution also equally important to decide the device performance in this case. So another one I can say so far I talk about the inorganic one. I just give one example for organic whole transport layer. So carbazole is one of the good organic whole transport layer. So this one is will quote on the ITO, because this phosphonic acid can have the good binding on the ITO layer. The COH group bind on the ITO and make a very well nano layer. When you have this nano layer, it have a very good homo level adjustment. Comparing to ITO, it have a very good homo level, and comparing to P dot also it giving a high level homo. And we make a device using the PM6, PDB6, and we can hear the device performance without any interlayer. You got only 6%. With the P dot is a standard device 15.9, but with the polycarbazole layer, phosphonic carbazole, we give 16.6. So comparing to P dot PSS, this carbazole layer giving efficient performance just because of not only for the monolayer one, this giving the energy level tuning. So by changing the energy level tuning, we can change the performance of the OPV devices. This is one of the example for organic whole transport layer. So far we talk about the moly oxide one, inorganic one. Like this I can talk about many layer. I just want to give one example, but all if you say that the same case will be applicable to remaining cases. Okay, and also everything the combinations is not for generic. Each material combination work for different interlayer. That one will come from according to how much optimization we are doing in the device fabrication. Okay. So now I go back to, so far I have done the metal oxide and small molecule one. Now we will go to electron transport layer. Electron transport layer, the metal oxide, I can give some family of electron transport layer. Here, metal oxide we can use zinc oxide, TaOH and tin oxide. This is a majority people used in this one. So in addition to there is other libraries there. This is a common one. And in the organic side, this is a PFN is also using, now instead of PFN BR is we can predominantly used because this N and bromine group is increases solubility in particularly in alcohol solvent. If you use in methanol, we can easily soluble rather than this one because of this the cationic and anionic group, it will dissolve the things easily. And PDINO, and also some of the polymer also is a PDINT, some of the polymer. These are all the family of electron transport layer. Okay. Okay. So we will see some of the example. As I said, in this one is metal oxide one. The metal oxide one is a zinc oxide is first dose. So in this one we have used this PTP7 as an active layer and BQR in the inverted one. We can see that this one will give the efficiency of 9.6%. Even the fill factor will go high. And also the same thing when you tie the ternary blend like PTP7 BQR, that time also we can get very decent performance at 10 point. Here we got an improved performance because because of mainly from increase in short circuit current. The increase is coming because of we add the ternary blend in this one. The ternary blend also will participate in the energy harvesting level. That's why we improve we can see the improvement device performance, and remaining other factors almost same, VOC and FF. And in this case we studied the difference in conventional inverter. This one we already said that one I have shown that on top of P dot PSS we do the TFE whole transport layer. Here we do the empty data is moly oxide. On top of moly oxide and below we have another data double layer like empty data below, that we can act as electron blocking layer here if you quote this one. And because of this double layer we can have the JSC improvement of 6.77 to 7.91 and the efficiency improvement from 5.8 to 6.34, this one. So this is another acting as a electron blocking layer because of the energy levels. And another one, you can say the electron. So in this device, what we have introduced one more double layer. On top of zinc oxide, we use PCBM BOH layer we introduce. That's because the zinc oxide layer, we always have a lot of defect state will be there, because there is unreacted oxide bond will be there, which will act as a recombination center, which will eventually reduce the performance of your devices. So we need to passivate the defect state in zinc oxide. To passivate the defect state, we take this PCBOH. This is a structure of PCBOH. We will coat on PCBOH on top of zinc oxide, and we passivate zinc oxide, and we see that that will passivation give the effect on improving the short circuit current and the fill factor and improve the device performance. And we can see that the improvement, the current improvement in the EQ of the device, and also we can see that the current is improving, not VOC, the current is improving because this surface passivation effect of this molecule. And this mainly because of this extra oxygen vacancies, this eventually defect state will be passivated in this device. Okay. So again we explore what's happening is when you do the double layer, the roughness is slightly decreased from 1.24 to 1.16, and also when you have this XPS data, we can detect the extra carbon. On the zinc oxide we don't have any carbon. When you coat it on PCBOH, we can still detect the 283 carbon atom one, but the PL quenching is one of the good signature of the surface defect passivation, because normally zinc oxide will emit green emission. If you have the zinc oxide, if you shine on the UV light, it will absorb the UV light and emit in the 520 green emissions. That's a good zinc oxide, but the emission is coming from the defect state. So that is defect is not good for your device fabrication, because that's a recombination center. So that one is greatly quenched when you coat it on this layer. So this is one of the effect how we can passivate the defect layer in device structure. So basically, if you want to have unwanted energy levels, that should be passivated in addition to aligning the energy levels of this interface layer. Okay. In other ways, we can have some other polyconjugated interlayers, because again on top of zinc oxide we use conjugated polyelectrolyte. Why we call it as a conjugated polyelectrolyte? These are all sulfonated sodium TEG, and we have the multiple oxygen group. So this multiple oxygen group make it more hydrophilic. So this type of functional group will induce a dipole on the surface. Again, if you have the more dipole is more on the electron rich compound is make us help us for electron extracting layer actually, because anything. So in addition to that, the CP layer will eventually passivate the surface defect on zinc oxide in addition to that extraction layer. This is another type of interlayer we can use on top of zinc oxide to efficiently block the hole on the inverted side. Okay. By using that one double layer, we can see the huge device performance from 9.7 to 10.3%, and the increment come from short circuit current as well as the fill factor as well. Okay. So this case is also when you do that by double layer, we can greatly reduce the dark current. You can see the dark current when you have the PFS DEG, the dark current decreased to more than 2 order. It come from 10 power minus 2 to minus 4. So the reducing of dark current is very important for the good device performance. Okay. And also we can see that you already gone through this impedance spectroscopy. If the series resistance in the device can be found in the impedance spectroscopy. So this the impedance plot will say that the series resistance will become greatly off of things ready. It's come from 6K to 3K when you coat on the top of the active layer. So this is one of the evidences to that when you have the double interlayer, the series resistance is also greatly reduced. So when you have the double interlayer, not only energy level is aligning, that is improve the electrical resistance, the decrease electrical resistance. At the same time, passivate the defect state. Okay. Defect state passivation is one advantage. Other thing is increase the conductivity, reduce the resistance. Both things are beneficial for the efficient performance of OPV devices, any organic solar cell. Like this, if you make small optimizations, finally we get up the big efficiency improvement in the device performance. Okay. So again we see that by doing this type of modification on the surface, we can have the roughness is greatly reduced from 2.9 to 1.3 here, and also we can see that the zinc oxide, when you coat second layer on top of it, the surface defect is greatly reduced in this case, because it's coming from that not only in addition to that energy level tuning, and surface defect also reduced here. And another option is how to get another one we have tried with this one is plasma depositions, because so far all the things we coated on spin coating layer, all the things, and to reduce the contamination effect, what we did is generate the plasma, the material we inject into the plasma chamber, then we coat it on the substrate, and we studied in device performance on top of zinc oxide. So on the plasma layer we will fully find the passivate defect state. We have used a different layer like thiophene, heptylamine and methylamine, all are amine state on top of zinc oxide, and all the cases we see that improvement. So this is another different method to make a passivation layer using plasma depositions. That's one more technique to make this ultra thin layer. Okay. And another things I want to tell, so far we have shown that zinc oxide is inorganic layer. I don't want to go through the TiO2 because all the same thing. I just to give one example. Same thing we can talk about for TiO2 and tin oxide. The lot of literature is available. Just one case, then I come to the small molecule one. In this case we use small molecule electron transport layer. That is this predominantly used PDINO and PDIN, and one more actually is PNDI based interlayers are popularly used in organic solar cell. Here you can use in this one P dot PSS and cathode interlayer, only one. We can see that the energy level tuning is very good, 3.64, and conductivity is very, comparing to that one to this one, is decently is good. So by using this device, we can have the device performance is going from 3.84 to even 16.78. So this is a very recent literature. This interlayer is reported just 3, 4 or 5 years before, and now we are using predominantly especially for making high performance device. Even the current 20% device, OPV devices making from this type of interlayer. And also this interlayer also making decent device stability as well. Okay. And in our lab we have also tried this type of NDA based interlayer. So here we synthesized the PDIN, just is a change of alkyl chain. Here is N group, we have the N functionalization here, here is only the alkyl chain. Here we introduced more polyoxyl alkyl chain. So by changing this level, we found that the band gap is changing by using this, but the core is same for all the cases, only the side chain. That will introduce the change in band gap, optical band gap here, and also energy levels are fine tuning, and finally we have the optimum performance energy level for PDIO things. And absorption wise is almost similar. In this case, we see that this device performance for PDIN, PDIA, and this one, we got a good efficiency for this PDIO, because if you see this one, the molecule, comparing to other one, this one have a lot of oxygen group is a p-oxy. So this will introduce a molecular dipole on top of zinc oxide, on top of active layer. This monoxide, this dipole will efficiently extract the charges, electron from the active layer. That's why we can able to see the improvement in particularly the fill factor is going away from 65 to 76 here if you see these devices on this one. And standard device PFNP are 11%. We got a very good efficiency in this case. And when we use a different active layer, even this efficiency go from 15 to 16.5%. So again, if you see the energy level for in this case, we can do that PDIN, we can see that how the energy level is changing. We have the when you have only PM6 ITF, only have low energy level. For PDIN, we have the work function is still become higher, and when you have the PDIO, the work function is still become low and low, because this is electron transport layer. We need to have a low work function metal for electron. Only for hole transport layer we have high work function. In this case we are getting low work function and also almost same HOMO, and this PDIO got a very low HOMO level as well. When you change this energy level, you can see that the energy level of this one is exactly matched to what is PDFN level, and this is very close to 4.3.95 is a good energy level match, which have a good electron extraction. That's why we can see the performance of these devices very high in the case of 16%, when other case we are getting only 15%. Again, it's all play around with the functionalization of the material, and that will eventually affect your energy levels of the material. Again, that energy level will specifically use for material in the active layer in such a way that we can efficiently extract the electron from the active layer to external electrode by using that interface layer. So that one we need to have a little bit knowledge about this band bending energy level arrangements. Then only we can make efficient devices. So like in this case, we compare these three interlayer, and we found that best is out of from PDI interlayer. In addition to that, the conductivity also is get improved, high conductivity for PDI interlayer. So like this, we need to get information. If you want to work something better, we find from a lot of data why this improvement is coming. Only is conductivity and energy levels. The other thing is surface, the defect state passivation. These are all the three things given by this type of interlayer. Eventually, this will contribute to the efficient device performance. That's what I was explaining to all these things. Okay, at least for each type of material and each one example with the device configuration. Okay, hope you can get how this interface layer will play a role for best device or best optimized device fabrication. So I convinced us so that starting from molecular design to and making device, what is a device architecture, including device architecture, and make a complete device. Because organic electronics is a lot of devices, as I said in the first class, many devices. At least I'm convinced that I should be able to make how the one device perfect. The same thing will applicable to any other device. Okay, because this is a very short course, we can't go through each and everything. That's why at least I can give one example device to make perfect. From that, it will give a more interesting for you to learn further. Okay, and this is a morphology effect, and as I said, I'll go through all those things, and then might be you will get a good gist of what is the importance of organic electronics, how it will going to change the future in things. Because as I said, this is a technology which makes the things from bulky to very small. Because eventually we are going to print it on paper or in plastic and more flexible. So eventually one day you can see the device become everything flexible and things. Particularly if we are expecting the functional device of OPV device. That's why currently we need to meet our carbon emission credit of, we want to have the zero emission at 2050. This is one of the technology can play a role in this reducing to save our environment. Particularly for using at least for, if the stability is an issue, we can use it for indoor purpose instead of outdoor. Because indoor we don't have that much energy for induce stability of this material. Okay. Okay. Finally, I would like to thank the group. Some of the work I have come up from my own experience, my own work. So this is a group we are involving. These are all the funding agency we got from mainly the Australian Renewable Energy is the main funder for our research, and this is our group. And then I would like to thank you very, very much for attending this session. And if you have any question, you can discuss now question. And also, even if you have any questions, you are welcome to write to my email. I'm giving the email address here. You are welcome to write me any questions. Okay. Now is the questions.